what if you could take a massive AI model, one that understands language almost as well as a person, and teach it a brand new skill in just a few hours? Well, that's the incredible power of fine-tuning. And today, we're going to break down exactly how it works using the Hugging Face library and why, honestly, it's changing everything.
Okay, so let's get right into it. The real superpower of these transformer models isn't just their fancy architecture, it's the fact that we can grab one that's already been trained on a huge chunk of the internet. This means they come to us with this deep, built-in understanding of language, which we can then just adapt for our own specific needs, even with way smaller datasets. And this slide really puts it all into perspective. I mean, look at these two paths. On one side, if you want to train a model from scratch, you're talking about massive datasets, unbelievable amounts of computer power, and weeks, maybe even months of training time. But on the other side, fine-tuning. You can take a pre-trained model, use a pretty small dataset, a single GPU, and get it done in a matter of hours. It's a total game changer for making this tech accessible to everyone. Here's a great way to think about it. The pre-trained model, that's like a world-class expert, a genius who already knows all the nuances of language. Fine-tuning is basically just you giving that expert a quick 5-minute briefing on your specific project. You don't have to teach them how to read or write, you just have to point all that expertise in the right direction. Okay, but before we can even think about fine-tuning, there's a crucial first step. We have to get our text into a language the machine can actually understand, basically numbers. And that process, it's called tokenization. So let's use a super simple sentence as an example. I am the walrus. Seems easy enough for us to read, right? But how does a machine, how does an AI model actually see these words? Well, let's see what a BERT tokenizer does with it. First, you'll notice it adds these special CLS and SCP tokens to mark the beginning and end of the sentence. But here's the really fascinating part. Look at the word walrus. The model didn't see it as one thing. It split it into 3 pieces, wa, ll, and rus. Those double hash marks just mean, hey, this is a continuation of the previous piece. This is how the model can handle words it's never seen before. It just breaks them down into smaller bits it recognizes. Okay, so that's how BERT sees the world. But what if we decided to use a different pre-trained model? Would it see that same sentence in the exact same way? Let's find out. And the answer is no, not at all. The XLM Roberta tokenizer gives a totally different output. The special tokens are different, and look, walrus is now split into wal and rus. This brings us to the single most important rule here. The tokenizer and the model are a matched pair. You absolutely must use the specific tokenizer that was designed for the model you're fine-tuning. No exceptions. All right, enough theory. Let's get our hands dirty with a real-world task. For our first mission, we're going to fine-tune a BERT model to classify news articles into one of 4 categories: world, sports, business, or sci/tech. Now, the beautiful thing about using a library like Hugging Face is that the process follows this really clear, repeatable recipe every single time. We load our data, we tokenize it, we define our model, we train it, and then we evaluate how well it did. It's a nice, clean workflow. So let's look at what our custom model actually looks like. You can think of it in 2 parts. You've got the body, that's our pre-trained BERT model. It's the big, powerful brain that does the heavy lifting of understanding text. Then we just bolt a new, simple head on top. This is just a basic classification layer that we train from scratch. Its only job is to take everything the body understands and make a final prediction for our specific task. So after running through those steps, how did our model do? An absolutely incredible 95% accuracy. Now let's just pause on that for a second. That means our model can correctly categorize 19 out of every 20 news headlines you throw at it. That's not just good, that is state-of-the-art performance, achieved by just giving an off-the-shelf model a little briefing. It really shows you how powerful this approach is. Okay, that was awesome. But now, let's up the difficulty. Instead of classifying a whole document, we're going to classify every single word in a sentence. We're going to fine-tune an XLM Roberta model to do part-of-speech tagging. You know, identifying words as nouns, verbs, adjectives, and so on. And what do you know? Look at that. It's the exact same 5-step process. Even for a completely different and much more detailed task, the core steps don't change. This standardized approach is what makes the whole Hugging Face ecosystem so efficient and powerful. But this new task does introduce a new challenge. Remember how a single word can be split into multiple subtokens? Well, that's a problem now. If we have one label, like noun, for one word, but that word becomes 3 tokens, which one gets the label? How do we handle that alignment? The solution is actually pretty clever.
The convention is to apply the real label only to the first subtoken of a word. For all the other subtokens that belong to that same word, we assign a special label of -100. This basically just tells the model, hey, when you're training, completely ignore these other parts. I only care about your prediction for the beginning of each word. Pretty smart, right?
So, with that clever alignment trick in place, how did our fine-tuned transformer actually perform? Well, let's put it head-to-head with an older type of model, an LSTM, to really see the difference.
And wow, just look at this. This is where you really see the magic. When it came to rare words like the tag for symbols, the older LSTM model really struggled, only getting 38% right. But our fine-tuned transformer, it sails through with 95% accuracy. This is because it can use all that knowledge from its pre-training to handle cases it's barely ever seen before. It's a massive advantage.
Okay, so that was for rare words. But what about the overall score for the entire task? Get this, a staggering 99% accuracy. I mean, think about that. For every 100 words the model analyzes, it gets 99 of them right. It has pretty much solved this problem. And again, this was done just by fine-tuning a pre-existing model. That is the power we've been talking about.
You know, the source material we're drawing from really says it best. For both of these tasks, classifying whole documents and tagging single words, the fine-tuned transformer methods just dramatically outperform all the older approaches. It's the perfect summary of just how valuable this architecture has become.
So, we've seen how fine-tuning lets us stand on the shoulders of giants. We can adapt these huge, powerful models for our own specific tasks with relative ease and get incredible, world-class results. It really just leaves us with one big, exciting question. Now that this kind of power is so accessible to so many people, what amazing problems are we all going to solve next?